This video is part of the derivation series for things that are out of syllabus but good to know. Today we're going to derive that the non-real roots of a polynomial equation, so a polynomial equation looks like this. The non-real roots of a polynomial equation with real coefficients occur in conjugate pairs. So let's say we have z is equal to alpha. Alpha is a complex number. So let's say this is a root. We can assume that this is also a root, the conjugate of alpha. So this is a conjugate pair. And today we're going to make sure the link between this conclusion and that statement is 100%. It works 100% of the time. Now, just to recap, the reason why things occur in conjugate pairs is because of the plus or minus symbol in quadratic equations. Now let's say we have x squared minus 2x plus 2. X is equal to negative b plus minus square root of b squared minus 4ac over 2a. Now this gives me 2 plus or minus square root of negative 4 over 2, which gives me 1 plus I or 1 minus I. Now you realize that the plus minus sign on the top over here is the one that gives rise to the conjugate pair. Because if the item in the square root, the number in the square root is a negative number, you're sure to going to get complex numbers within the roots. Now today we're going to prove that given one root, now let's say we're told that 1 minus I is a root, we need to confidently conclude that 1 plus I is also a root. We can confidently claim that, but we first need to prove that this link is true. So, well, without fail, we have to use the complicated equation on the first page. But it's basically a really simple idea that all these coefficients, so polynomial equation, all these coefficients an minus 1 all the way until a0, they're all real numbers, right? Where n is an integer that's positive, right? And all these z values, right, they could be real or they could be complex, but they're all elements of the complex realm because real is a subset of complex. Now, we need to prove that given a complex root, so let's say beta, for example. Let's say we're told that beta is a root. We need to assume as the final conclusion that z is equal to beta conjugate is also a root. Right, so now we have to substitute. So step 1, we need to substitute z is equal to beta. And that's an b to the power of n plus an minus 1. Now just to recap, all these a's are all random coefficients of the z terms. Right, so they could be 1, could be 2, could be negative 0.1. It's all possible. Okay, and now we're going to take the conjugate on both sides. So left hand side, okay, let's just bracket over here. Conjugate, 0 conjugate. Right, but the conjugate of 0, because 0 is equal to 0 plus 0i, the conjugate is 0 minus 0i. So essentially it's equal to 0. Now we're now going to prove that this on the left hand side is equal to an bn conjugate plus an minus 1 bn minus 1 conjugate, so on and so forth. We've got to prove that the conjugate of these, the one conjugate of all these, sum of the terms is equal to sum of the conjugate of all the terms as well. I don't know if that sounded confusing, but so basically we've got to prove that z plus w, right, the conjugate of z plus w, where z and w are both complex numbers, is equal to the conjugate of z plus the conjugate of w. Now let's say z is equal to a plus bi, and w is equal to c plus di. Now we have left hand side is equal to a plus bi plus c plus di. A conjugate. Well, that gives you a plus c minus bi minus di, right? The real part minus the imaginary part in this case. And that's equal to a minus bi plus c minus di. which is the sum of the conjugates of both terms. Right, and by including another term, now let's say Q is equal to E plus Fi. Right, there won't be any issue because you're just going to slot it in here, and you're going to get the property proved either way. So first link is done. That's conjugate of the sum of the two complex numbers is equal to the sum of conjugate of both terms. The next step is to we've got to toss out the B conjugate. So we've got to expand out the conjugate. Right, it doesn't look possible, but I'll show you later. So we got to expand out the conjugate. Okay, is equal to 0. So the proof that you need here is, the second proof that you need here is the conjugate of ZW. Right, in this case, you see Z is over here, W is over here. So the conjugate of that must be equal to conjugate of Z times conjugate of W. So let's try to prove that now. ZW, whole thing conjugate, is equal to Z conjugate times W conjugate. Left hand side is equal to A plus BI, using A and A, B, C, D again. A plus BI times C plus DI, whole thing conjugate. Right, you get AC minus BD plus CBI plus ADI, whole thing conjugate. So that's the real component, AC minus BD, minus the imaginary component. So all changes to negative. And I'm going to factorize out the C in this case, giving me my Z conjugate over here. And what I'm left with is negative D times B plus AI. Right, but what I want is a W conjugate, so I need to have DI in this case, DI. So I have B over I plus A. Now take note, B over I is equal to, I'm going to multiply it, going to realize the denominator. I have BI in the top, and the denominator I have negative 1. So that gives me B over I is equal to negative BI. So I get C A minus BI minus DI times A minus BI. Right, and using grouping, I have A minus BI times C minus DI, which gives me what I really want, which I've proven the property over there, that ZW conjugate is equal to Z conjugate times W conjugate. Now all I need to do is to simplify this whole thing. I remove all the conjugates of the real terms. Right, that one is really self-explanatory because the conjugate of a real term, so let's say 3 conjugate is equal to 3, right? A real number's conjugate is equal to a real number itself, because there's no imaginary component to be concerned with. So we'll remove all these conjugates. And we're almost there. We need to make this look like this over here. So we got to ensure that let's use a different color here. A n b conjugate to the power of n. Right, so this directly substitutes z to b conjugate. Right, we got to swap the positions of the conjugate and the powers. So the one final proof that we need to make is that, I guess you can see it by now, b to the power of n to the power conjugate is equal to b conjugate to the power of n. The conjugate of b to the power of n is equal to b conjugate to the power of n. And we know in the complex numbers in polar episode, or the video, if you haven't watched it, really encourage you to watch that video. The Argand diagram. Now b is located, let's say it's located up here. Right, so it's a modulus of r and an argument of theta. And the b conjugate is in the opposite direction, so it's negative theta with magnitude of r. Now it's reflected about the real axis because the real component of the conjugate is the same as the actual and a complex number itself. So the left hand side is equal to b to the power of n conjugate, and that's equal to, now b is equal to rei theta, in this case to the power of n with a conjugate. So that's equal to r to the power of n ein theta conjugate. And we know that the conjugate of a product of zw is equal to product of z conjugate and w conjugate. We know that it applies here as well, right? The conjugate of r to the power of n times conjugate of ein theta. And this is equal to r to the power of n, because r to the power of n is a real number, so it has no conjugate whatsoever. And e to the power of in theta, well, if that's the argument in this case, the conjugate must be equal to e to the power of negative in theta. And that's equal to re negative I theta to the power of n. Right, and re negative I theta, with the argument of negative theta, is equal to b conjugate. It's the whole thing to the power of n. So knowing that the polynomial equation of degree n has n roots, and all the coefficients are real, take note, all the coefficients must be real, then given that z is equal to beta is a root, you can conclude 100% of the time that b conjugate is also a root.